Oh, thank you very much, Bob. It's a pleasure to be able to talk to you people. What I'm going to talk about tonight is a talk based on one that I gave last April at a conference in Paris. What they had there was a conference on the physics of sports, and it turned out I was invited to talk about the physics of sailing, and it turned out that I was the only one talking on that subject. The talk was originally designed for a group of physicists, few of whom knew anything about sailing, whereas here I have a group of sailors, some of whom maybe know something about physics. So I've modified the talk a little bit accordingly. The first part of this talk will be very generalized sort of theories of sailing, and the first thing I'm going to talk about is this: what are the constraints on air and water to make sailing possible? And you'll see what I mean by that shortly. Then secondly, I'm sure you can all answer this: why must a sailboat make leeway when it goes to windward? And finally, I'll talk about how does the flow of water and air produce the forces that propel a sailboat. I mean, most people often think, oh, the wind blows on the sails and it pushes it along. But of course, that's not what really happens unless you're going flare off straight downwind. Normally, the wind blows around the sails and produces a force. And so how come it can produce a force under those conditions when it's just moving around the sail? So that we'll explain as we go through. So in order to, and that is hot air ballooning. You know that if you get in a hot air balloon, this is a hot air balloon going over the land just north of where I live at Long Bay, and if you get in a balloon like that, especially if there's a westerly wind blowing, the balloon will of course move with the wind, and if you were in the balloon and had an anemometer, it would read 0 because you're moving at the same speed as the wind. Okay, so in that location with the westerly wind blowing, it would not be long before you found yourself over the sea. So when you look down, from your point of view, you would see the sea streaming past. And you might say to yourself, well, I'm sick of just not being able to control this thing. I'll put a water sail down into the sea, and I'll be able to direct the balloon in another direction. So by that means, you would be able to make the balloon go through the air to waterward, which of course is exactly the same as what a sailboat does, except that the roles of air and water are reversed. So the whole thing is going to look like this. So here's our balloon, and we start going across the landscape at Long Bay, and before very long we reach the sea, and so we do this. There's the water sail, and off we go in a different direction. So the lessons to learn from that: what are constraints that make controlled sailing possible? And that is that there must be a relative velocity between the two media that the boat is immersed in. The one is the air with the sails, and the other is the keel and the hull with the water. And those two media must be moving with respect to one another. If they are not, controlled sailing is not possible. Okay, so let's now go to the next question. Why must a sailboat make leeway when it's going to windward? I'm sure you all know, but and I don't need to define what leeway is. That was for the benefit of these French people, some of whom were not sailors. In order to explain this in a slightly different way from normal, let me do what physicists like to do, and that is conduct a thought experiment. Excuse me, I need some of this stuff. A thought experiment is a wonderful thing because you can do anything providing it obeys the laws of physics. So in this thought experiment, we have here a boat which initially is not moving. You can imagine it's tethered to, or it's got an anchor, or it's alongside a dock or something. But the sail is set and the wind is blowing, and so these green lines, of course, and I'm sure you've seen pictures like this before. The green lines indicate the flow of air around the sail, and I'll talk a bit more about that in a moment. And that flow of air produces a force, which is represented by this arrow here, which we call a vector, and that's the direction and magnitude of the force produced by the sail. Well, that you all know that happens because you have sails and you put them up and you see the effects. Okay, so initially then, that's the only force acting on the boat, so therefore the boat goes in the direction of that force. If you push something this way, it goes that way. If you push it this way, it goes that way. So the boat must go in the direction of the force, which is more or less sideways. And this diagram's a bit confusing because this thing is meant to be a dock. But anyway, forget about that. So as soon as the boat starts moving sideways, of course, then there's a flow of water around the keel, and that flow of water is represented by those blue lines there. Because the boat is almost going sideways, the flow is very turbulent, and so the keel and hull produce only a small force represented by this blue arrow here. So now you have two forces acting on the boat. You've got this blue arrow, and you've got the original sail force there, which is always going to be present. And so those two forces add together to produce this purple force here. And if you remember physics from school, you can figure this out by what's called a parallelogram of forces. But it's intuitively obvious, I think, that if you push a little bit that way and a lot that way, the resultant is going to be something like that there. Okay, and then, so now the boat is moving slightly more forward than it was before. And so the flow of water around the keel is greatly improved, and so the keel force now is greatly increased. And so we have this force, that force acting, and the resultant of the two is the purple one here, which now is almost pointing forward. So the boat is now starting off going sideways and then more forward, as I'm sure you've all experienced under these conditions. And finally, then we get to a situation where the boat is moving forward, and the flow of water around the keel is producing this keel force here, which is exactly equal and opposite to the sail force. So at that point, there is no net force acting on the boat. But of course, that condition only arises because the boat is moving forward. And of course, it's kind of hard to believe that there's no net force acting on a boat which is pounding to windward and the mast is about to break and waves are coming over. But taken as a whole, there is no net force on the boat if all those forces are added up together. Let's see, here's an animated version of that. Here's the boat starts off and it's moving away and eventually finishes up with two equal and opposite forces. The fact that these two forces are equal and opposite is part of the reason why my book, which is over here, is called The Symmetry of Sailing, because of that symmetry between water forces and air or sail forces, which is always present in that situation and in others. Let's see, what have I got here? Okay, so in order to develop a side force, that is opposed to the sail force, the keel must have a small angle of attack, and this angle of attack, of course, is a leeway. So I think just going back to that diagram, if the water flow were straight down there, then the flow around the keel would be symmetrical, and so the forces each side would be equal and opposite, would cancel out, and so you would have no force here, and you would be back to the boat going sideways again. So you must have an angle of attack of water on the keel to provide the asymmetry which produces that force. Okay, well, I'm sure you are all pretty much aware of that. So now let me go back down to this question here, which is slightly more complicated. How does the flow of air and water produce the forces that propel a boat along? Well, we should define a couple of things before we do that. Physicists like to define things a bit like lawyers, I suppose. Here we have a sail, a wind blowing in this direction, and that sail produces a force like that, a sail force. In order to simplify things, we at first make it more complicated by introducing two forces. The drag force is defined as a force in the direction of the airflow, and the lift force is defined as a force perpendicular to the airflow. And these two forces, of course, add up to the total sail force. So we can either look at the total sail force, or we can look at these two, or because they are right angles to one another, we can look at them separately, because the force at right angles to some direction doesn't have any effect. It's a bit like pushing a railway wagon along some railway lines. If you push it at the back, it moves along. If you push it at the side, it's not going to go anywhere. So these two forces are independent of one another, and that's the value of using two separate forces rather than the sail force itself. We are interested only in this lift force. Drag, of course, is very important, but for the purpose of understanding why you get a strange force at right angles to the direction of flow, when you think about it, you've got wind flowing this way, and normally if you stand in the wind, you feel it pushing you along. But with the sail, the force is at right angles to that direction. So it's, when you think about it, that's a rather odd thing. And so we want to be able to explain how that comes about. So, and for the purpose of the French audience, even the asterisks couldn't explain that.